In this example, we will be talking about linear regression or multiple linear regression. So this part is going to be, or this example, we will go over three main points. The first point, in the first recording, we will be building the linear model, or at least a linear model, one model. In the second part of the recording, or in another recording, we will be building, or we'll be assessing or building other models and assessing these models and do some comparison between the models and choose the best one. And in the third part of the recording, we are going to assess the model assumptions. We will go over the assumptions. And we will be covering just one example, and we are going to do everything in one example. The example says we have a website, Realtor, is analyzing the relationship between, I don't know if it's Realtor or TAR, I don't know. Anyway, it's a website for real estates. Is analyzing the relationship between the sale price of a home, which is in dollar, square footage, SQFT, this is the variable, is defined that way, number of bedrooms, beds, number of bathrooms, baths, and colonial as a dummy variable. If the house has a colonial style, it's going to be 1, otherwise it's going to be 0. So we have the data file already. We have 36 recent home sales. So we are trying to study the relationship between the price and these independent variables. So the very first thing to do is loading the library and import the data, and we did this many times. So this is my data. The second thing to do is just look at your data, view your data. We have price, square foot, beds, baths, colonial, and all of these are numbers in numeric, which is fine. But again, we have to explore the data. We have to look at the data type first. All of them are numeric, which is perfect. Again, we need to have numeric when we study the linear regression. When you do linear regression, if you've seen something like a character or something, you have to do transformation, as we did in chapter 2. Change it to numeric using one of the three methods. It depends on the variable. If it's nominal, if it's ordinal, if you have to do a dummy variable like this one, colonial, it was maybe yes or no. Then we change it to 1, 0, because 1 is colonial, 0 is not colonial. This is a binary variable. So the first part is we have these, and we would like to estimate the linear model. Estimate the model, this is the question. And if you notice here, I'm using dollar signs. Do $2 and you have something in the middle, then ending by do $2. This is LaTeX when you want to write math equations. If you'd like to write math symbols, math equations, fractions, etc., we will be discovering these. In every class, in every recording, maybe you're gonna see something like this. We use either single dollar sign if it's in line with the other text, or if you'd like to start a new line, you can use $2, so the equation appears in a new line in the report. So what is again, I'm using \beta because beta is a Greek letter, so \beta give you the beta underscore 0. So this is you will be learning this gradually. So this is the linear model is defined that way. The price as a function of the size of the house, number of beds, number of baths, and whether the home is colonial or no. And the idea is we would like to form sample regression equation. We would like to do a prediction. We would like to estimate this. So this is the point, is estimating model. So the estimating model, we have to write this down. The estimated model will be of the form, you can create dollar sign and type all of these to get this one. So this is the estimated price. This is what we are going to produce. So this is my original, or the linear regression model that we would like to estimate. Because we don't have access to population, we have access to sample only. We are estimating these. Betas, we are estimating betas by B's, B0, B1, B2, B3, B4, right? And how to do this? We are going to create chunk. We're going to call it linear model, L model. We're going to create the model now. We are going to create the model. We are going to study we are going to build the relationship now, or to see the relationship, okay? How to build the model? We are going to, the linear model, we are going to use a function, very important function, you have to memorize it, which is LM. LM contains many arguments. For now, we care about 2 arguments only. You have to write first the response variable. Again, let me just go back here. Sorry, let me stop here a little bit. Let me go back here. This is your response variable, the price. And these are your independent variables, okay? So first response variable is the one that you are trying to predict, is the outcome, is the response. And others are the independent variables that we maybe believe that the price depends on some of these or all of them, maybe, right? And yeah, it makes sense because, I mean, the price depends on the house size and beds, baths, and actually in the location. Location is not here. But anyway, this is maybe a study in one location. Anyway, so LM is a linear model function. So we are going to use the first argument is going to start with what? With the response variable. Then we're going to use tilde. Then you're going to write all of the independent variables, all the variables that you believe that there is a relationship between them and the price. In this case, the question tells you that, hey, please give me the relationship between the price and all of the variables. So that's fine. Because all of the variable, you can write SQ. You have to stick to the names, by the way. Plus bids, plus baths, plus colonial, right? Comma. This is the second argument now. Yeah, but I mean, okay, we have a price, we have square root or a foot, beds, baths, colonial. From where? From my data. So this is the linear model. Two arguments. Because you're using all of the variables, all of the independent variables, you can use another method, which is just delete them and dot. So replace all of the variables with dot works, okay? Or you can keep them. So if you'd like to study the relationship between the price and beds and baths only, you cannot put dot. So dot includes all of the predictors. By the way, I'm not saying that you have to study this and this. No, when you're building a model, the very basic thing that you do is you are trying to see the relationship between all of the variables, mostly with the response variable, all of the predictor variables with the response. Then you try to take off some of them or minimize them or something like this. So now I'm going to do what? I'm going to simply take this and see the model. So L model. So I'm going to run this. I run it already. So it's L model here. It's a list. And I'm going just to see the L model now. So it gives me this. So the one that we already wrote, this one, the predicted price equals B naught plus B naught is the intercept. B1 is the coefficient of the square root foot. B2 is the coefficient of beds. B3 is the coefficient of baths. B4 is the coefficient of the colonial, right? And we have all of these coefficients here. So this is B naught, this is B1, this is B2, this is B3, this is B4. It's just mathematics. So you have to plug in all of these numbers instead of B's. So now we have an equation. We have a nice equation. So we have this now, right? So if you plug in all of them, we got this. We got the estimated price is going to be $165,888.66 cents plus $91 times a number of the square foot plus $4,372 times number of beds plus $66,619 times the number of baths plus $74,000, etc. times whether it's colonial or no, 1 or 0. So the colonial takes values 0 or 1. Baths takes values 1, 2, 3, 4, 5, etc. Beds takes values 1, 2, 3, 4, etc. Square foot takes square foot, like 1,000, 1,500 square foot, 2,000, etc. Right? So this is my model. So this is my estimated model. So we have created the model right now. Now we're going to move to the second thing, which is, okay, what does it mean by all of these guys? What does it mean? So let's interpret the coefficients. Okay. What is 165,888? What does this mean? Okay, this is the estimated value of the price when all independent variables, all of them, are zeros, which is like the baseline price of the house when all of the other variables are not considered. If you don't consider any of them, if all of these are zeros, so the baseline of the house is 165 without thinking about all of these guys, right? So this is the first interpretation of B naught. So the intercept, we can say, what about the second one? The second one, which is 91.68, the coefficient B1. This says or indicates, this is important to understand again how to interpret these. For every additional square foot in the house, the estimated price is expected to increase. Why increase? Because it's positive by $91.68. And there is a statement I have to continue. Assuming all other variables are held constant. And I have to stop here a little bit. Hold constant hold constant all other variables means, when you interpret the coefficient of any variable, we are isolating the impact of that variable on the price, but keeping all other variables constant. That allows you to understand the specific influence of one variable on the dependent variable, on the price in this case, without the interference of changes in other variables. How can we explain this? Suppose that you have two houses, and they are identical in terms of number of bedrooms, number of bathrooms, and whether they are colonial or no, they're identical. But one has more square footage than the other one. So we expect the house with the more square footage to have an estimated price that is $91 higher for each additional square foot. This is the meaning. If you're comparing, so we are holding every predictor of variables as a constant, then we are just focusing on this. For any additional square foot, this will increase $91. Okay. So this is the square foot. This is the B2, right? So this is the B1, sorry. It's a B1. What about B2? Where is B2? B2 is, we have 4,372. For each additional bedroom in the house, the associated increase in the price is going to be 4,372. Excuse me. So each additional bedroom in the house is associated always with an estimated increase in the price of what? $4,372. Again, we have to continue assuming all other variables are constant, right? Next, what is B4? B3? No, this is B3. Let's go to B3. Yes, B3. B3 is about what? Is about baths now. For every additional bathroom, or each additional bathroom, is associated with an increase in price of 66,619, assuming all other variables to be constant. And again, this is B3, right? The last one, which is 5, B4, the value. These are the B's. These are this is the B, right? So this means that if a house is a colonial style, the estimated price is expected to be higher by $74,557 compared to a non-colonial house, assuming all of the variables to be constant. And this is the way that we are interpreting all of the coefficients. After that, after interpreting, what we are going to do, we are going to do some prediction, okay? Now we are not assessing the model. This is important. We don't know whether the model is good or no, not yet. But we would like to predict a house price. You go to a certain area, specific area, then I give you the size of the house, number of beds, number of baths, and I tell you whether the house is a colonial or no. Can you predict the price for me? Yes, we can, based on the model that we have built. So how to do this? We are going to use the predict function to obtain predicted values from the model, okay? So, I mean, it's just simple. You can do this using your calculator. I give you the values, and you can plug in these values into this equation. That's it. Square foot, how much I give you? 1,400, where is it? Yes. 4 beds, 3 baths, and non-colonial size 0 here. So you have just to plug in these values here. Then you calculate mathematically, you get the price. Let's do this in R, because this function is very important, very nice function. First of all, what we're going to do, we are going to use two functions. The first one is creating a table or data frame, because sometimes you would like to predict more than one values, not just one value. Maybe you're going to just do a prediction for more than one value, right? So first of all, we're going to create a data frame like a table. It's like a table, data frame, okay? The first is going to be the first, we stick to the names of the variables, SQFT. Again, case sensitive, so we have 4 beds, we have 3 baths, and the question says colonial equals to 0. So I just create a table, okay? This is a table of these values. And I would like to do what? I would like to, maybe I'm going to call this table by, I don't know, you can just call them P, okay? P. And I would like to use a function, very important function. We will use this function every time from now on then, called predicts. For now, predict, we're going to have 2 arguments. Predict has many arguments. We're going to use now 2. Sometimes we can use 3, 4, depends on the context, what we are going to use it for, okay? Predict, we're going to first say, what is the model that we built? It's called L model. is the first argument. The second argument is going to be your data frame. What are you going to predict? Okay, it is P, right? So the first one is the model. Use the model or use this equation and plug in these, plug in these values into this model. This is the meaning of predict now. Then you run the second one. Oops, we have a problem. SQFR. SQRT is wrong. SQFT. Here we go. So what is the price of that house? The price of this house is $511,582.3. So it's kind of $500,000, right? So this is the price. Let me go further a little bit, okay? Let me do something. Let me create another data frame. I'm gonna call it X, okay? I'm gonna call it X. I would like to do, I'm gonna copy this, okay? I would like to have not just one value. I just would like to predict many values, not just one. Do you remember what we do? We just put them in vectors. So C, I would like to predict, I close the parentheses, two houses with different sizes. The first one 1,500, the second one 2,400 or 2,500 square foot. Then the two houses, the first one again with 4 bedrooms, and the second house is with 5 bedrooms. The third and the baths, I'm going to keep it 3. Both of the houses 3. You can keep it 3 or you can create a vector C, 3, 3, the same thing. I'm going to keep it 3 as is. And the first house is a colonial, the second one is not. So C is going to take a value of 1. The second one is going to be not colonial. Remember, just make sure that you close the parentheses. Look, it's kind of a shaded here, right? The parentheses, the opening and the closing parentheses are closed, so we are good. And I'm going to predict this again. Predict, plug in the X in the L model. So don't forget to run each. These are the prices for the houses. The first one is about $586,000. The second one, about $62 or $616,000 or $17,000. It's just about this, right? We can go further, but I'm not gonna go complicated now. I'm not gonna put them into like a table or something. You can put them into, use CAT as we did before, CAT to report, okay? You can put CAT to report. You can use many methods. I'm not gonna go into deep stuff here, coding, so I'm gonna make it simple. You can leave it like this. You can write this by your hand there, down there. You can write this here, narrative, just write some text. So a house with, you can say a house with 1 square foot, I don't know, 4 beds, 3 baths, and a colonial style, or we can say a colonial style house with this is estimated to be priced by $586,142.40. To, if you like to use a dime, be careful. Why? Because this is going, maybe it's going to give you an error or no. Put it into math context. How to put into math context? Use $1 before, $1 after. But because we have something here, because we're using the $sign as a currency, I'm going to use backslash. Okay, look at this. We can see it here. So it's within math context. The number is within math equation because I use $sign at the beginning, $sign at the end, and we have a $sign that represents the currency. It starts by backslash. Okay, so a colonial, yeah, I mean just to report. Okay, next. This is nice. After that, we are going to construct a confidence interval. What is the confidence interval? The confidence interval, if you remember, is the estimates. We are creating the estimates in the range, or the range, in which the population mean is likely to fall with a certain level of confidence. Okay. In this case, we are going to do what? We are going to construct 95% confidence interval for expected price of 2,500 square foot, colonial style home with 3 beds and 2 baths. Okay. We're going to create an interval now. Again, there is the same function. It's a very powerful function. Predict, small letter. We start with a first argument, fine, and the second argument is the data set as we had before. I'm going to copy it. I don't want to keep typing these. Okay, data frame. Oh, is it possible to write the whole thing inside, or I have to define it as a variable p? Then no, you can, as we did before, you can copy it, you can put it in the second argument as a function. That's fine. Comma, but the question says 2,500 or 2,500, sorry, and we have 3 beds and 2 baths, and it's a colonial style, so it's 1. So this is the second argument, which is, do you remember, it's like the p value or the data frame value. After that, we're going to have another argument called the level. In this case, the level is 95%, so it's going to be 95%. It's the confidence level. We have to have another argument called the interval. We have two types of intervals here. Now we're going to find the confidence interval. So we have four arguments for this predict function now. Enter or run. So we have values now. We have the fit value, we have the lower bound, and we have the upper bound. So what is the fitted value? Is the predicted or fitted value of the response variable of price. In this case, it's estimated to be $615,990 for a house with 2,500 square feet, 3 bedrooms, 2 bathrooms, and being a colonial style house. The lower bound and the upper bounds, these are the 95% confidence interval of the predicted value. So the 95% confidence interval suggests that what? We are 95% confident, that the true value of the response variable, the true value, is going to fall within this interval. We are 95% confident. I mean, I don't like to use this term, but that's fine. The 95% confident that the true value of the response variable falls within the interval between $65,000 and about $67,000. Okay, because this is one sample. We just had one sample now. If you take any other samples with these values, the price is going to be between these two numbers, 95%. I mean, if you take 100 samples, 95 of these 100 samples will have the population mean within the interval. This is the meaning of that one, okay? So you can actually say this. You can write this down, I'm skeptical to use this term here because it's not like we are confident. No, I mean, the way that I explain this is important. We have a problem with the dollar sign, so what I'm going to do, I'm going to add dollar sign before the number. This is backslash, close it here. Add another dollar sign here, backslash here, close the dollar sign here. Then we're good. Look, numbers. Nice. Here we go. Now we are going to do what? We are going to build prediction interval. What is the prediction interval? Is the estimates, the range in which a new individual observation is likely to fall within a certain level of confidence. As we said, if you have a new observation, the new observation is going to fall between what and what? This is the question, okay? And the question says, do the prediction interval using the same numbers. If you have a new value, where is the new value is going to be? The price. If I give you a house, 2,500 square foot, colonial style, 3 beds, 2 bathroom, what is the prediction of the price is going to be? In the confidence interval, let's just make the difference between two. The confidence interval give you the mean, the expected value, the expected price, the mean, okay? The mean. The estimated price of the population mean. But here we are creating a prediction interval for the new values, okay? So that's why we're going to do the same thing, and we're going to do the same function, by the way. I'm going to copy this, and I'm going to go down, but guess what? I'm going to change only the confidence into correct prediction. 3, 2, 1, I think we have the same stuff, right? The fitted value is the same. It makes sense because this is the predicted value. It's the estimated value. If you take these numbers, if you take 2,500, 3, 2, 1, plug them into the equation, you're going to get 61,000, right? But we have different boundaries, lower and upper, right? We have different. The prediction gives you a wider range. When we expect an individual, a new observation that falls between 95%, so we are going to get a wider, a prediction interval than the confidence interval, okay? So in this case, the new observation or the future observation is going to fall within $466,000 and $765,000, okay? So we can say this. Again, let me add a dollar sign, backslash, dollar sign, backslash, dollar sign here, then we're good. So this is everything for part 1. Next recording we will be doing model selection.